This is the final video for Unit 5. It's actually just a sequence of about 3 review questions, just reviewing the idea of the accumulated area function. And we're going to jump right into it here. We're on this page right here. It's an old AP exam question where they gave us a graph and even a few isolated points where we can actually see the y values. It's a graph of velocity versus time. And let's see what it says here. The graph of velocity versus time in feet per second of a car traveling on a nice straight road is there for 50 seconds. And they've even got the 5-second interval times over on the little table on the right. First question was, during what intervals of time is the acceleration of the car positive? So it's not the same thing as the graph. The graph is velocity, and they're asking us questions about acceleration. But that's totally doable because, just thinking about the physics, the acceleration is actually just equal to the slope of the graph. Okay, it's the slope of a velocity time graph. So really what they're saying is, that acceleration needs to be positive. Can you find out when that's happening? Sure, well that'll happen when the slope of the graph is positive. So that's just something we can look at visually right off the graph. And it looks like the slope is positive all the way up to 35. And then it's positive again from 45 all the way to 50. It looks like some flat spots in the graph at 35 and 45, so it's not actually got a positive slope there. It's got zero slope there. So if I was given my answer, I would probably say, well, at 0, that definitely has a positive slope, and all the way up to just before 35, maybe not at 35 though, and then after 45, but maybe not 45, up to and including the very end time there of 50. Okay, well that first part wasn't so bad. B, find the average acceleration. Okay, so again, we're working with a velocity time graph. So if we're going to try to find the average acceleration, we're going to have to do the average slope, the average rate of change, right? That's going to be our strategy here to find that average acceleration. And so really, to find this average, sometimes denoted with a little bar like that on the top, I'm basically going to go back and just do a little grade 10 slope calculation. If I can do it right though. It's going to be a y2 minus a y1 all on top of an x2 minus an x1. Except this time, it's actually going to be a velocity 2 minus a velocity 1 all over a time 2 minus a time 1, because this is a physics story. And so I do nothing more than go up to that table and start just peeling values right off the table. And in this case, it looks like my second velocity at time 50 is actually going to be 72, and my first velocity was 0, and then I'm going to divide that by a second time of 50 minus a first time of 0. And when I tried that out, I ended up with 1.44. The units for that would be feet per second squared. Right? Feet per second would be a velocity, and then feet per second squared would be the acceleration. So far this AP exam question is going pretty nicely. Nothing too serious yet, but there's a few more parts. This one here, find one approximation. So it's not going to be perfect. We're only going to be close, so kind of accept that fact. It's not going to be a perfect thing. For the acceleration at time 40. Okay, well let's go back and look at this graph and this table up here to see what's going on. We're definitely trying to find some sort of instantaneous acceleration here at time 40. We basically need the slope of a tangent line. It's kind of what we're after. All right, so if I was to go up to time 40 and draw in some sort of tangent line like this, that would be finding, if I can find the slope of that, the instantaneous acceleration for this thing at time 40. Well, they're giving us a value that is actually a point in the table, right? Like there is actually a spot right here at 40. So you've actually got 3 choices because this table is beautifully symmetric with 5-second jumps. You could go from time 35 to 40, or you could go from time 40 to 45, or you could even do the symmetric one and go from 35 all to 45. Those are all perfect options in this story. I'm actually going to go for the symmetric one. I'm going to go from 35 to 45. Okay, again, key thing, if they want to know the actual acceleration right at time 40, we're trying to, well, we're going to approximate it, but we're going to approximate the instantaneous slope, right? The instantaneous rate of change, and that's what we're after here. So the best I can do for that, well, I've got those three choices, but I like doing the symmetric one in this case. I'm going to do the velocity at time 45 minus the velocity at time 35, and then divide all of that by 45 minus 35. Grabbing numbers right from the table, 60 minus 81, all sitting on top of just a plain old 10. And when I tried that out, I ended up with a negative, which makes sense. The slope of that tangent line looks negative there. Negative 2.1. And the units, just like last time, they're going to be feet per second squared, being an acceleration. Okay, we're moving along through this question. It's not taking too much time. This part might slow us down slightly. It says approximate the integral of the velocity with a Riemann sum using midpoints of 5 subintervals of equal length. And then using correct units, explain the meaning. Well, I can tell you the meaning right now. If you integrate velocity, what that's going to do is tell you how much you've moved during that time overall. This is going to be the displacement. Now, if all I say is the displacement, that's probably not going to earn me a mark on the AP exam. But I could say the displacement from time 0 to time 50. Now I'm talking about what's actually happening here. Okay, but let's go back and look at the picture to see how we're going to accomplish this displacement calculation, right, where we're going to be estimating the definite integral. They wanted us to use 5 intervals of equal length, and we're getting to 50. So each one of them is going to have to be 10. So I'm going to just set up a little picture here, get this rolling. It'll take me just a second. Okay, so I've got these rectangles I'm going to try to add in, and I want to make sure that I raise them up until their midpoints touch the graph. That's my plan. So there's 2 of them in. Here's the third. Again, always raising them up until their midpoints touch. So I'll be grabbing those midpoint y values in order to accomplish this. Is this going to be perfect? No, but it's the best that I can do for now. So okay, thinking about these intervals, they are 10 seconds wide, and then we're going to be multiplying by feet per second. So we're going to end up with feet every time we calculate one of the areas of these boxes. And they're all 10 wide. Okay, I'm going to have to go and grab those midpoint values. So I'm going to be grabbing like this 12 for this box right here. Like that one is 12 tall. And then I'm going to grab the 30, and then the 70, and then the 81, and then finally the 60, right? Like this one right here is 60 tall. Okay, and this first one is 12. Okay, well, let's go and try this out. See what we've got here. Looks like this displacement, it's going to be 12 feet per second times 10 seconds plus 30 feet per second times 10 seconds plus 70 feet per second times 10 seconds, and just a couple more of these, 81 feet per second for 10 seconds, and finally 60 feet per second times 10 seconds. I'm liking the way these units are going to be working out here, right? Because this is feet per second multiplied by seconds. So yeah, this is going to be in feet. If it's helpful to you, what you could do as an option is you can imagine factoring out, sorry, let's get rid of this here. Go away. There we go. You could imagine factoring out, hang on one second, so I have to get this ink back. Okay, there, sorry for the glitch, I think we're back. If it's helpful, one of the things you could do is factor out that 10, and you could say, hey, is it faster for me to calculate things this way? 12 plus 30 plus 70 plus 81 plus 60, all multiplied by 10. I'm lucky all those intervals happen to be the same length. That might be a little bit quicker for you to figure out. The answer ends up being 2,530, and the units would be feet. And again, what you figured out is the displacement, okay, just highlighting that again up here, you found the displacement from time equals 0 all the way to time equals 50. So don't just say, oh yeah, I found the displacement. You want to say, well, what displacement, right? The one that occurred from time 0 to time 50. And just a little reminder here, okay, a little physics reminder. If you want to justify that some sort of function is increasing, then one of the things you can do is you can say, hey, well, I've noticed that the derivative is positive. If you have a function where the derivative is positive, then the graph is definitely increasing. The arrow doesn't quite go the other way every time, but that's definitely true. You can justify something's increasing by doing that. Now for physics, if you want to justify that an object is moving to the right, then what you want to do is say that the velocity is positive. So you've got a couple of options there. Really all you need to do is just say that the velocity is positive. Because the velocity actually is s prime. Right? So when you're saying, oh yeah, well the derivative of position, it's positive, that's the velocity. So it's good enough to just say the velocity is positive. Okay, well that's the first of the three that we're going to take a look at. The next one is one of these little chipmunk gathering area deals. Okay, so this was from an old AP exam. Let's just kind of get comfortable with the story here first, and then we'll start tearing apart their question. Okay, I've gone and grabbed my little chipmunk area gatherer, like a chipmunk gathers nuts for the winter. And it says this graph of the function consists of just a couple of line segments. Okay, great. And that's f of x. And then g. G is going to be this accumulation, right? So it's not the same as the picture. It's the gathering of nuts from some starting time until whenever you want to stop. And it looks like in this particular story here, we're going to be starting right at 0. Okay, so this is kind of a key thing to pick up on. There's our start, and so that's right here, right where my little chipmunk is right now. He's ready to gather nuts up for the winter, and we'll see what kind of value we get. And so right off the start, they're saying, okay, can you go and find g of -1, g prime of -1, and g double prime of -1? And I'm going to go and get myself my legend all ready to go. So it's looking like we've got g being this antiderivative of f, right? This integral of f. So I'm going to set up my legend here and say, okay, if they ever want to talk to me about g, I know how I can interpret that with the picture. That's actually the integral of f dx. Whether I use x's or t's doesn't actually matter, right? So this is the area of the pick. Okay, moving on in my little table here, my little legend. If they ever want to talk to me about g prime, no problem. If I take the derivative of an integral, if I do the derivative of this integral right here, that's going to get me right back to just talking about the function again. So that's the fundamental theorem of calculus. G prime is just going to be nothing but the picture. And then if they want to talk to me about g double prime, if they really want to do that, not a problem. I can just think about f prime. Okay, that's just the slope of the picture. Okay, here we go. So g of -1, that's actually the hardest part of this first question. G prime of -1 and g double prime are super easy. I'm going to split my page up here a little bit, give myself some room. So I'm going to put a line just in here. Maybe another one here. Just kind of divide up my workspace a little bit. Okay, so the first one, probably the most challenging. Trying to find g of -1. According to their instructions, g of -1 is an integral from 0 to -1. Whoa, that little chipmunk's going to have to back calculate. F of x dx, or you could say f of t dt. Makes no difference what that variable is. That's sitting right here and here, any variable you want. Well, that's a little bit weird to integrate backwards. that creates a negative sign generically. So let's start dealing with that. This is going to be the opposite of integrating from -1 to 0, f of x dx. So what if there was a little chipmunk integrating from -1 to 0? Let's go and look here and see how much area they'd gather. They'd be gathering up area all in here. If we're going to go from -1 to 0, that would be a positive walk, and it's a positive function. So that area is positives times positives. It's a positive area for sure, and it's actually just a triangle. So this is not too bad, and I've got my negative sign already hanging just on the outside there. Right, so this negative came because it was a negative walk for the chipmunk. Now, here's my area calculation. 1/2 the base times the height. Okay, well that one wasn't too bad. It wasn't super exotic. And so we end up with -1.5. Probably the hardest part, right, of part A. Part B is actually going to be a lot quicker. If they want to talk to me about g prime of -1, that's the exact same thing as f of -1. It's just the picture. I just go and grab a value from the picture. And so I do exactly that. I'm going to go to -1, find the y value. It looks like it's 0. Okay, easy enough. So g prime is 0 there. And then g double prime. Okay, let's go for that. G double prime of -1. Well, that would actually just be f prime of -1. That's just going to be the slope of the picture, sitting there at -1. Okay, well I have to think about what that's going to be, right? We got a line, it runs over 1 and then rises up 3, so it looks like it's +3. Excellent. Next question, what do they got for us here? Per B, for what values of x from -2 to 2 is g increasing? And then explain your answer. Well, here's what I'd be thinking. If we want to talk about g, which is actually this area gathering function, if you want to say g is increasing, what we could do is we could say, with the exception of some possible little flat spots, it looks like g prime is going to have to be positive. But g prime is actually just the same thing as f. So we're just looking at f, which is the picture, and we're saying, hey, that's going to have to be positive. If you ever find a spot in this picture where f is positive, technically actually the arrows go this way. If f is positive, g prime is positive, and that would mean that g is increasing. So looking back at the picture, when exactly is this function positive? It looks like in between -1 and 1. Now, it would be perfectly okay to say, here's my answer. It's going to be in between -1 and 1. If you think about that whole issue of like, well, what if the graph goes from a flat spot up to like this? It's, technically increasing on that whole interval that's in there. It is actually okay, right? If you wanted to, it's even a little bit better if you could say from -1 to 1 hard edges, but it wouldn't matter. You could have either soft edges or hard edges. It's not a big deal. Okay, and then they've got a couple more questions here. Same picture, just there as a courtesy for you. In fact, let's go back and bring in our little area gathering chipmunk. Okay, so he's sitting there gathering area starting at 0. And it says, for what values of x on that open interval is the graph concave down? And then explain your reasoning. Well, here's what I'm thinking. I'm going to do this kind of backwards. I'm going to say if g is concave down, then that means g double prime must be a negative. Now I say this is kind of backwards because really a negative second derivative tells me that it's concave down. But that's all right. Just working this logic in reverse. G double prime is the same thing as f prime of x. F prime of x is just the slope of the picture. And apparently, I want that to be negative. If that's negative, then I would know that g double prime is negative, and then I would know that g is actually concave down. So all I have to do is just look and see, where's this graph decreasing? Where's the slope negative? And that's pretty easy to find. It looks like for that whole second half. Now, in order for it to be concave down, it does actually have to have a negative second derivative for g. So that would mean that f prime has to be negative, and zeros wouldn't quite work out. So we're actually going to say that the answer for this is the interval after x equals 0 and then on to 2. And then we'll say soft edge on that, because they said at the very beginning of the question, they said soft interval here from -2 to 2. So we won't try to grab 2 in this story. They had one more little request of us to see if we could sketch the graph of g from -2 to 2. Sure, we can do that. We've got a couple of points we could put in. I'm just going to go back and look at our little chipmunk gathering here. When x is 0, if you were to put 0 in here, the chipmunk would not have gathered anything, so there'd be no nuts at all. So g of 0 would be 0, and we've already found that g of -1 is -1.5. By the exact same reasoning, if the chipmunk was to go forward and start with no nuts and walk this way, it would gather up 1.5. So I've actually got a few points I can put in onto this sketch already. It looks like, with high confidence here, I can put in a point right there and say, well, you got no nuts there, -1.5 at -1, and you would have 1.5 at 1. Now, some other things that I'm noticing. Looking at this story here, it looks like, if I can go back, once we get past x is equal to 1, we're going to start actually integrating and creating negative definite integrals. Like all in here, this triangle will take nuts away from the 1.5 area of nuts that we'd gathered there. It's a beautiful little bow tie. And by the time you get to 2, you'd be back down to 0. And I can even do the same logic here and say, well, if the chipmunk had -1.5 units of area there, when it does this double negative walk, a walk in the negative direction with a negative function, that's 2 negatives, that would add to my graph. So I've actually got an addition back to 0 here and a drop down to 0 there. I'm going to have a local minimum at -1. I know there's a local minimum there because I can see the graph. If I'm thinking about g, its derivative, which is f, is going to make a change in sign at -1, and it'll make a change in sign at 1 as well. So this graph actually looks kind of like this. That would be my sketch. Okay. That one's all wrapped up. Let's try one more of these little chipmunk gathering ones. I'm going to go grab my chipmunk so he's ready to go for the last one. All right, number 3. Let's see what we have here. The function f consists of a semicircle. Okay, it could be a little more challenging for finding area. And 3 line segments. Let g be the function defined by the gathering of area underneath f. Oh, interesting. This one is a lot more challenging. This one starts at -3. So we better put our little chipmunk like way down here and say, okay, chipmunk, you are going to begin gathering nuts right there. That's when you have no nuts, and then you go and gather from that point. I'm going to set up my legend as well right now. They're telling me that g is actually the integral of f, right? It's the area underneath f. Or you could say it's the antiderivative of f. That means that g prime, if we have to talk about it, is just f. It's just the picture. And g double prime, if we want to talk about that, would actually be f prime. Okay, so it's going to be the picture's slope. It's picture prime. Okay. First thing, we have to find g of 0 and then g prime of 0. Well, the g of 0 is the one that's the most work. So I'm just going to make some space here and say, all right, I need lots of space to do g of 0. Maybe not so much to do g prime of 0. So g of 0, if that's what they want me to do, then they're asking me to go and find the integral from -3 as a start to 0 underneath f. Whether I write of t or of x makes no difference at all. All right, well, what's that going to look like? Okay, let's look at this chipmunk going for a little walk here. It's starting here, and it's going to go for a walk until 0. So it's going to be doing a positive walk because it's going to the right, and it's a positive function, so it's going to be a positive answer, that's for sure. But it's a trapezoid, and I'm going to have to very carefully think about how that area is going to work out here. But it's doable, right? We've got some sides to this trapezoid. One of them is 2, and the other one is 1. We're going to have to average those, and then multiply by the width. So we could say, okay, let's just average those heights. Maybe I'll call them h's instead of l's. I've got height 1, height 2. I'm going to average those up and then multiply by the width. So I'm going to be averaging 2 with a 1. Try to average this correctly, though, by dividing by 2, because there are 2 numbers, and then multiply by how wide it is. I'll multiply by 3. So what do we got here? So we're 1.5 on average tall, multiplied by 3. This is going to be an area of 4.5. The next part, oh, so fast. You want to find g prime of 0? No problem. That's the same thing as f at 0. It's just the picture. So I go and I look at the value of the function at 0, and the y value is just a plain old 1. Super easy. Okay, part B. Find all values of x. We don't have to find the y values, which is nice, but find all values of x in the open interval, so we don't have to worry about endpoints, which is nice, where g attains a relative maximum, and then justify your answer. Okay, well, if we're going to have g of x being a maximum, then based on the first derivative test, I can say, hey, that's going to happen if g prime of x is either equal to 0 or does not exist. We're going to have a critical point, right? That'll be important. And not only that, we're going to have to be looking for a place where g prime switches, right? If you want a maximum, then g prime is going to have to make a switch. It's going to switch from a positive number to a negative number at either a place where it's 0 or a place where it's broken. But hang on, g prime is exactly the same thing as f. So it looks like f of x is going to have to switch from positive to negative. And during the time that it's switching, it looks like f is either going to be, that is the worst looking bracket ever. F is going to have to either be 0 or does not exist. So let's just go and see if we can find a spot where that happens. Are there any places where this graph switches from positive to negative inside that interval there? Well, it comes down and it touches 0 right here, but it doesn't switch. It doesn't switch actually until there at x is equal to 3. That's the only one that I would go with. I wouldn't go with this one. That one there I think actually is going to be some sort of relative minimum for g. But the second one is great. I would say, yep, here's my answer. X is equal to 3. Okay, so far so good. Just got one last page here. So they got a couple more questions. There's the little courtesy graph again. Let me go and grab my area gathering chipmunk. Okay, so this chipmunk starts at -3. That's making it a bit of a challenge, but we're up to it. And it says find the absolute minimum of g on the interval from -5 to 4. Okay, so it's got hard edges, so we will have to consider the endpoints. And then any interesting values along the way. If you want g to have a minimum, okay, then by the same logic that we had done before, if g is a min, then g prime is going to switch. It's going to switch from negative to positive. But g prime, of course, is the exact same thing as f. So there's one possible place that I might want to go and check out, and that would be at -4. That would be some sort of local minimum. I have to also consider the endpoints. I have to think about what they're going to be like. So I'm off on a bit of a quest to go and compare these various values. I've got g at -5 to think about. I've got g at -4 to think about. And then I should go and check out the very end of the deal. I should probably also go and check out g at 4. My absolute minimum is going to be hiding somewhere in there. Okay, well, this first one is the chipmunk gathering area up from -3, that was its start, to -5. The area underneath f of x. Let's go look at that. I think we're going to be able to do this one pretty quick. If that chipmunk goes and gathers area from -3 to -5, in here, as it does this negative walk on a positive function, that pink area, as far as a definite integral, will come up as a negative. And then you end up with this part, where the chipmunk is gathering up area by doing a negative walk with a negative function. That would be a positive area. And that beautiful little bow tie is just going to cancel out, and it's going to add to 0. So the value for this function at this spot, the value for g at -5 is just 0. That's not too bad. Okay, well, what about g of -4? That would be half of that bow tie. That's actually going to have some value to it that isn't 0. We're going to be integrating from -3 to -4. Okay, well, that will be a negative walk on a positive function. That would be just this pink area here. It's just a triangle. It's got a height of 2 and a base of 1. So I can figure out, sorry, jumping around here. Computer's not being super nice to me this morning. There we go. I can figure out what this area is going to be. It'll just be 1/2, a base of 1, and a height of 2. But it's negative because we're walking backwards on that function. So that is a -1. Okay, so far this is the better deal. We've actually got a more negative number than we had at g at -5. So this is a lower value. It's more of a minimum. The only thing we have to check out now is g at 4. That's going to involve having our little chipmunk integrate from -3 all the way up to 4. And we're going to see what kind of answer you can get. -1 is our lowest so far. It's our best minimum. Now let's go and see what it would be like to go for a little chipmunk gathering area walk, starting at -3, because that's where this one starts, and then finishing all the way down the road at 4. Well, there's some area to be gathered here. Okay, so there's that area, which I think we've already done. And then there's a little bit of area under this circle. And then it's interesting. Then there's this bow tie. This section right there, that actually adds to 0. So, you know, if you were doing your AP exam, you could maybe mention that you're not even going to bother with that section, but you'd have to mention why, right? So maybe down here you can say, well, one of the things I'm going to point out is that the integral, just throw it in here somewhere, you could say, hey, the integral of that function from 2 to 4 underneath f dx, that's actually 0. So I'm not even going to do that section. So really all I have to do is the section in blue. It's clearly going to be a positive answer, so it's not actually going to be a very good value for trying to come up with a low answer. But let's see if we can find that area. So for the circle part, right, we're kind of looking at it. Think about it this way. What if you've got a square with a little circle inside? And this square is apparently 2 wide, and so the radius of the circle is 1. If you want to look at the area of all of these corners, like all 4 corners together, you could go with the whole square, 2 squared, and then minus the area of the circle, which would be pi times radius squared. So that's actually 4 minus a pi, right? That would be the area of all 4 of those little circles in there. Okay, well, what we need to do now is take only half of that, because we've just got 2 of those corners. So that would be, if we're going to do half of it, that would only be 2 minus pi over 2. That would be the area of these 2 little corners in there. And we've already figured out earlier how much area there was on this trapezoid section. Okay, we did that one. That one was 4.5. This is definitely going to be a positive answer. It is not going to be the best minimum. So I'm kind of wasting my time here a little bit, but that's okay. 4.5 for the trapezoid. That was the integral from -3 to 0, plus this new little section, which is going to be 2 minus pi over 2, which is clearly positive, right? And so this best answer, if I was to say, hey, I need to come up with one answer here, it's this one right here. That is going to be my absolute minimum. So it'd be -1. This last part actually goes pretty fast. Find all x values inside the endpoints, not worried about the endpoints, where the graph has an inflection point, the graph of g, pretty nice, easy to do. If g of x is an inflection point, then that tells me that g double prime has to be switching. I don't care whether it switches from positive to negative or from negative to positive, but it's got to do one of those. Okay, well, going back to my legend, what's g double prime? Oh, there it is up upper right. G double prime is just f prime. It's just the slope of the picture. Okay, so we're looking for a moment when the slope of the picture is going to make a change. So that would be f prime. So the picture slope, that's going to have to change. And it's going to change from positive to negative or from negative to positive. Either one. So I'm just looking for a place where the slope of the picture makes a change in sign. All right, coming along. Oh, positive slope on the picture, changing to a negative slope at -3. That's one of them. Looking for, oh, not here though. Here, we go from a negative slope to a negative slope, so not at 0. Oh, but definitely at x is equal to 1, we go from a negative slope to a positive slope in the picture, and then again at 2, where we go from a positive slope to a negative slope. So my answers for this one would be, you're going to have inflection points on G at x is equal to -3, 1, and 2. Moral of the story on these little chipmunk area gathering stories, set yourself up a legend right away. Right? They're super helpful. So just looking back at the beginning of this question here, these legends, they are amazingly helpful to sort out what's going on in your story. The worst situation that you have to find yourself in is actually integrating the function to find the area. Sometimes you got to work with weird shapes like circles and trapezoids and stuff like that. It's actually nicer to work with the G prime and the G double prime, but especially after you've set up that legend. So do that first, and then I think you'll find that these little chipmunk area gathering questions are actually pretty doable.